Today I'm going to be talking about conformal prediction, which is, how I explain, it's been a topic of my PhD and I've been promoting it for a number of years, and now it's a very popular topic, so I'll tell you what it means a little bit later. But maybe just to introduce myself. Oops. Okay, so my name is Valeriy. So I'm a data scientist, so I did a PhD in Royal Holloway, University of London, which is just outside of London. It's actually part of the sort of several universities which comprise University of London. I think it's like 8. So I did a Master of Science in Computational Statistics and Machine Learning in UCL, which is here in London, and studied basically machine learning over there, and then I decided to do PhD. So I started PhD in 2015, supervised by Professor Wolf, who is the creator of the Conformal Prediction framework that I'm going to be talking about. A curious fact, he's also the last PhD student of Andrei Kolmogorov. So when I did my PhD, I did a number of research projects published in some leading machine learning journals, such as Journal Machine Learning Research, Machine Learning Journal, so on and so forth. And after I have finished my PhD, essentially, I have created a resource which is called Awesome Conformal Prediction. So it's actually reached 4,500 stars before hard reset. It's basically back to 600, so 5,000 plus together. And it's kind of created a lot of momentum behind the topic. And if you look into kind of Google, Google and search for the kind of dynamic of the topic, just went exponential basically. So I published a book back in 2022, which is on applied conformal prediction, and 2 new books were just released. They are for early release, so they're still in progress. One on advanced conformal prediction, and the other one is time series forecasting, which is another of the topics I'm very passionate about. So today I'm going to be talking about conformal prediction. This is broadly an overview. So I'll talk about probabilistic prediction. First of all, what does it mean? Why do we need it, and where is it used? I'll talk about probability calibration, which is a topic that was quite unknown a few years, but nowadays it's kind of becoming very popular as well. And then I'll talk about conformal prediction, kind of various settings. If you're familiar with machine learning, there are various kind of use cases, but broadly they can be classified to classification, where we're sort of predicting a binary label, a regression, which is continuous label, or time series. And then I'll talk a little bit about the kind of developments outside of table data, in particular things like LLM, NLP, computer vision, so on and so forth. So why are we interested in probabilistic prediction, right? So, if familiar with machine learning, essentially what we are mostly interested about in predicting, sort of given the labels of features, right? We want to predict Y, and Y could be a label, whether it's a cat or dog, or Y hat could be, for example, demand for a product, which is continuous, right? So essentially we are interested in mapping X to Y, which is a majority of cases. Of course, there is also things unsupervised learning where we do clustering and other things. Historically, before kind of machine learning came to the fore, people were using statistical techniques. So you're probably familiar with things like logistic regression and linear regression and things like that. And they were initially invented for kind of low scale, low dimensional data before computers were even around. So things like linear regression, logistics regression have been around for 100+ years, right? So they're not new. In around 2000s, because volume of data started to increase, so internet appeared and a lot of data started to come through, people realized they needed more powerful methods. So initially things like support vector machine, which is Wapnik invented back in Soviet Union in the 60s initially. That was a linear support vector machine, and then in the 90s they expanded it to kind of non-linear cases. But in the 90s also very popular models that we use today, like random forest appeared, and also You're probably familiar with things like CatBoost, XGBoost, which is essentially implementation of boosted trees that have been around since 90s as well. So the issue that we have is that quite to this day, a lot of cases, people are just interested in point predictions, right? So if you want to predict the temperature, what is the temperature going to be, right? So we build some model and we just kind of make a educated guess, right? So the issue is that we don't know how the reliable prediction is. So, you know, if you predict temperature of, I don't know, 16 degrees tomorrow, is it like 14 to 20 or 14 to, you know, 17? So we're going to talk about it, what it means. But in many situations, people are interested in quantifying uncertainty around these predictions, right? So how do we do it in a smart way? So just to illustrate the point, here is like two cases. One is from health industry, right? So we imagine a situation, we have a patient and we have a doctor who has scans of the brain, right? So it could be X-ray, it could be MRI scan, and the doctor needs to decide whether the patient has life-threatening disease. So for doctors, they need a couple of things actually, not just interested to say, okay, is the likelihood or not of, say, brain cancer, but they're interested in both including and excluding conditions with high certainty, which means they want to understand how certain we are that patient really has or no, doesn't have cancer, and perhaps if there is no cancer, is there anything else like concussion, for example, right? So they're interested in these kind of things. Here is an example from self-driving cars. Somebody mentioned today working with self-driving cars. This is also like very kind of critical application, because one of the things that self-driving cars need to do is to detect obstacles on the road, right? So they need to know, for example, is there a pedestrian on the road or not? I'll explain today that most, if not all, models are miscalibrated, which means they don't produce correct probabilities of prediction, right? So for this particular case, we would like to know how confident we are when the model is saying there is no pedestrian on the road. And, you know, the probability that there is pedestrian on the road quite high, we probably stop, right? If it's uncertain, we slow down, and there are like other sensors and systems that we can use. This picture is actually from a talk by Michael Jordan. That's not a basketball guy, right? It's a famous researcher, probably #1 machine learning researcher in the world. So he was in Berkeley before. Now he's also in Henry in France. Very short talk. I quite like it because it's 10 minutes. You can get like a lot of information about why we are doing things like uncertainty quantification. So I mentioned in machine learning we have certain kind of use cases, right? So if you are working in the industry, you're familiar, most of companies in kind of real industry, not Google or Facebook, they're interested in tabular data, right? It's like 80% of the cases. They want to do things like using machine learning for classification, for example, predicting whether a customer would churn or not. Or if you're in financial services like a bank, you would like to know whether the transaction is fraudulent or not. This is like classification refers to kind of discrete outcomes on the label, which is 0, 1, or perhaps a few more classes. We have prediction, which is normally we refer to as kind of predicting continuous label, for example, a demand for particular good. And kind of class of prediction problems is time series, right? Because we have sort of points in time and we want to predict what's going to happen. This could be pretty much a lot of applications from you know, monitoring, for example, cloud to predicting demand in almost any company, to things like, you know, predicting signal on the sensors of a machine or things like that, right? So what kind of unites all these situations is that we would like to go from point prediction to one step more, where the machine is actually able to reason about how uncertain it is about its own predictions, right? So we not only want a point prediction, but we want the machine or like model to tell us, you know, if I'm saying there is no pedestrian on the road, how confident I am in this prediction. So this is actually a quote verbatim from this first paper from '98. So this was like when the first paper was published about conformal prediction by Gamerman, Wolf, and Wapnick, who was also like one of the founders of machine learning department in Royal Holloway. And essentially at the time it was called learning by transduction. So conformal prediction appeared like 5 years later when they published the first book. The topic was pretty much unknown for a long time. So when I started in 2015, there was like an annual conference that's on this particular subject, and there was like researchers from the whole world. You could fit them in a small conference room. So it was mostly people from UK, some people from Sweden who learned about it pretty early, and a few people from Greece, Italy, and Russia, and that was basically it, right? So such framework was, it's very valuable. Explain why, but was unknown for a long time. So now that we, want to quantify uncertainty, we would like to understand where uncertainty is coming from, right? So there are like certain sources of uncertainty, and it could be with the data, to do with the data or the model, or just things like noise, right? So let me just explain. There are two classes of uncertainty people usually talk about if you hear about it. One is called aleatoric uncertainty, and this is uncertainty due to inherently random effects. For example, stock market and things like this. There is a lot of like stochasticity, so it has high aleatoric uncertainty. On the other side, there is, here you see there is low aleatoric uncertainty. There is certain structure in the data, so we can actually model it quite simply with linear regression. That's the first source of uncertainty, to do with the data and how much randomness there is in the data, right? The second class of uncertainty is to do with epistemic uncertainty. As I believe this is coming from kind of Greek word for knowledge, and this refers to our knowledge about the system, right? So if we start to learn about the system, like for example, if we are in the physical world, we have a pretty good understanding of physical events, right? Like Newton, was dropping the apple. We know what laws describe the situation. If you are dealing with socio-economical phenomena, there is no like fixed laws, right? But as you accumulate more data, you learn more about the system, and you're able to actually reduce this epistemic uncertainty, right? But aleatoric uncertainty is kind of inherent in the system, so some systems have more uncertainty than others. So the natural question before I go, people try sometimes estimate one or another, and when we talk about conformal prediction, just to understand what we are estimating is the whole uncertainty event, right? To do with the data, how random is the data, how good is the model, and what's the level of noise. So it's actually capturing everything in one. Yeah, please go ahead.
Yeah, I'm not quite sure I understand the difference.
Differences, yeah.
Between aleatoric and epistemic. What
Yeah,
do you mean?
yeah.
There is a certain line of thought that randomness is a way to model what we don't know.
Yeah.
And therefore, aleatoric, which is due to random effects, is essentially epistemic, which is due to lack of knowledge.
Yeah, I mean, I know what you're talking about. So there is, some people might argue there is like blurred border between them, right? But in terms of like very, very basics, this is like what people usually talk about. Say, in this case, we have a structure, right? So the aleatoric uncertainty is pretty low, right? If we take some event where we can actually model the data with, with a good regularity, it's quite, like for example, we know like when the sun is going to rise tomorrow, right? Pretty well. That's a low aleatoric uncertainty, right? If we look, for example, at traffic patterns, right? We know that people are driving in the morning and in the evening, and also like at weekend, right? But if we look into some like situations during the weekend, if there are certain events, it's becoming like less certain, right? So it's just it's a framework. There's no like hard or soft science here. It's just a framework to understand, because you might if you deal with this uncertainty kind of, you will probably hear this. When I first started, I could never remember these terms. I just kind of thought about it, but now because I'm teaching and writing books, I kind of try to remember. So let's talk a little bit about probability calibration, and this is also like very, very important topic. So I've been promoting conformal prediction for years, probably since 2016. Like nobody paid attention for for the first 3-4 years, I would say. Calibration is the same, nobody cared. Nowadays it's a big topic, and I'll explain why. So essentially, this is to do with, we can use the word calibration for both like classification and regression, and I'll explain what good intervals mean, but here it's more like you probably hear about it like in a classification context when we predict a label, and then we say like we make a bet, right? Somebody mentioned we make a bet, and we say this particular horse is gonna win, right? And then you put it in data in the model, something comes out. How do we know that this is like a real probability? So calibration is all about making sure the probabilities are real, right? They're not just coming through the box, and we want to have like real probability in kind of frequentist notion that if we say there is a rain, like 70% chance of the rain, then it's going to be 70% chance of the rain. So we talk a little bit about what is calibration, how do we measure it, how do we actually make sure our predictions are calibrated, and how we can calibrate predictions. So I explained to you that all, like the way I teach students is like they ask, which models are calibrated. It's a kind of the current state of the knowledge, and like years of research, like 20 years of research have shown that all models are miscalibrated. So you should treat any model as uncalibrated. So you need to check the calibration, and you need to try to improve calibration, especially when it matters for you, like when there is self-driving cars or like health or even like betting, yeah. And I'll tell you what Facebook does as well. So calibration is like, I tried not to throw math, but this is like, very simple formula if you're familiar with probability. So what we want to achieve is to make sure that whatever class score, and deliberately don't use probability, because if you look into scikit-learn, for many years they said it's actually probability that models produce, and the reality is they don't. It's actually a very misleading term, predict proba in scikit-learn. So they recently started to change this documentation because it's like momentum is shifting and people are saying actually this is not probabilities. So what they produce is class score, right? 0.7 means score indicating there is more likely class 1 than 0, right? So we say that model is calibrated when predicting for certain like buckets of probability, say 70% chance of rain. If you predict it for 20 days or like 100 days ahead, for these events on which we predicted 70% chance of the rain, we actually computed the fraction of the rain occurrence would be 70%, right? It's very simple as that. So it's actually just making sure that our kind of model produces probability in line with reality. Very natural and simple definition. So curiously enough, none of these concepts are new. So people are kind of adopting them now in machine learning, right? But the people who invented a lot of these things were the guys, right? So they did it like back in 50s, and the reason they did it because they produced forecasts, right? And they say like 70% chance of the rain. They started to think deeply about it and like saying, what does it actually mean, right? What does 70% chance of the rain mean? And if we produce forecasts, how do we make sure it's a correct kind of forecast in terms of probabilistic forecasting, right? So this guy, one of these weather kind of researchers, Glenn Breyer or Breer, I'm not quite sure. He created the way to measure the quality of the forecast. And if you look at this formula, it's kind of in a very small font. But in reality, it's basically like quadratic error, right? If you're doing machine learning, you probably know like mean squared error and things like this. So instead of just continuous labels, we compare like label 1 or 0 with probability, and we kind of sum them up together, square, and see if there is discrepancy. This is like one of the metrics that people use for checking calibration and making sure the models are correct. It's a very good metric, so I'm not going to deep dive into details, but it's one of the metrics that is known as proper scoring rule. And proper scoring rule is basically, if you're interested, I recommend to deep dive. Kind of probabilistic prediction is a kind of a science. There are like people, professors who specialize in it. And it can be proven mathematically that if you're using proper scoring rules and your model is producing honest forecasts in line with underlying distribution, not something else. Yeah. So the question could be, does calibration even matter, right? So hopefully I convinced you by now that if you have MRI scan then we need to know whether 90% chance of no cancer is correct probability. It's not 80 or 60 or 95, right? Or self-driving car, you know, if we say there is no pedestrian on the road, we want a good probability which is calibrated. But what about like well, I shouldn't be saying non-consequential applications. Applications that don't involve like a risk to human life or like health, right? What about like, say, if you are approving a loan or a mortgage, right? Are we like bothered? And it turns out that we are, because, you know, if you issue a mortgage, you want a correct probability of default, right? So you can evaluate, say, you know, somebody comes to the bank and they say, okay, I want £250,000 mortgage. The difference between 4% default and 6% default is big, right? So difference. So the banks want a calibrated probability. And sometimes you see, like on social media, people would say, okay, it actually doesn't matter if we are just doing ranking, right? You will see like arguments. People say, okay, if you're doing like churn basically means we try to predict whether the customer would leave or not, right? And they say, okay, and I've seen this, you know, in 2018, I went back to the industry. A colleague of mine was building a churn model and just kind of scoring the relative likelihood of people leaving. But if you think about it deeper, such predictions are kind of meaningless, right? Because business people want to know if customer X leaves, how much money is they going to lose, right? They want to know exact probability of customer leaving and how much customer is worth, right? You can't just say, okay, I know these 10 customers are leaving, because you have like resources are rare in the business, right? You need to know exactly how much money we are talking about. And if you've been in the data science for some time, you would realize actually that quite often, you know, new data scientists make a mistake that they're kind of interested more in a model and kind of complexity rather than talking business language to people, right? So you need to talk business language to people who understand finance, and kind of finance is universal language. Dollar means dollar, pound means pound, right? So to do that, you need a calibrated probability, right? So, and connected to that, you probably noticed more recently there is a lot of momentum towards like explainability. People talk about explainability, so this is part of that. If you don't have correct evaluation of uncertainty, your kind of explainability is very shaky. A number of frameworks like European AI Act and other things, and also like industrial regulations in banking in particular and health, also kind of steer you towards having good probabilities of prediction. Fairness, also very important. If somebody applies for a mortgage, nowadays people expect them to be explained why they were denied a mortgage, for example, right? So you need to know exactly what the probability and why it was reduced like that. So essentially, to trust any predictions, especially in consequential applications, you need to know how certain they are. So here's to illustrate with kind of scenario that doesn't affect human health. And I just created this because, you know, I see sometimes people, nowadays not so many anymore, you know, like good data scientists know that the calibration matters, but before you would have, okay, it doesn't matter, let's just do ranking, right? So it's a very simple problem. You have a portfolio, say it's like a bank or hedge fund, or you have 250 million and you need to invest into portfolio A or B, right? Just one of them. So imagine you run a model. It could be a fancy model which produce 3% estimated probability of default on one. Then you just multiply one by another and you have expected loss, and naturally you want to minimize the loss, so you go for this one, right? So now we know that all probabilities are miscalibrated, and I'll tell you a bit more about the research. Imagine that we actually calibrated the model and we have slightly different, you know, it's not even like a big difference, slightly different outcome. You see the decision outcome is completely reversed now, right? So we're not investing into portfolio B now, we're investing into portfolio A, right? So, yeah. How do we measure and how do we like understand whether models are calibrated or not? Quite simple way to do it. I mentioned we can use Breyer loss or Breyer score and also log loss, right, which you're probably familiar with as on a kind of separate subject, but you can actually use log loss to also check your calibration. But one of the ways, don't rely on it, because if you're relying on pictures, it depends upon the buckets and everything. But one of the ways to visualize it, it's quite simple kind of reliability diagram. So all you need to do is essentially for your posterior kind of scores or probabilities produced by your model, you calculate actual outcomes, like in this case of rain, 70%, if you predict 70% chance of the rain, what is actually the occurrence of the rain? In this case, it's 90%, right? So you see there is mismatch, right? It should be like this, 45-degree line, but it's kind of mismatch that way usually, or that way, depending upon the model and the data. And quite usually, deep learning in particular is like overconfident. What does it mean? If I say there is 70% chance of the pedestrian on the road, actually it's probably 50% or 60%. So it's kind of inflating probabilities towards what they are not, right? And this is this case on the right side. Yeah.
I'm not quite sure I understand. So we have this model. We have data.
Yeah.
How do we get to these pictures?
How do you get to these pictures? You have a test set, right? So on the test set, you predict probabilities of classes 0 and 1, and you know what the real label is. So quite simply, you just for each bucket of predicted probability, say around 10%, you take this bucket for these objects and you calculate the frequency when the label was 1 for this.
I take all the cases when the output is like 60% plus minus 5%.
Yeah.
And I calculate, and that would be the empirical.
Yeah, this would be the empirical accuracy, right? And here, this is your model accuracy.
And then I just
yeah.
I calculate the frequency.
Yeah.
The posterior probability would be the frequency of the label.
No, posterior probability is produced by your model, and here is it's kind of the other way around. I'm just normally if you go to scikit-learn, this is what you produce, right? So the key to remember is like when people talk about overconfident or underconfident, the way I teach students is you start here, and this is like a fact. You can't change the fact. So you're just comparing this number with this number, and if it's over, that means overconfident. So it's inflating probabilities compared to what they should be. I hope it's clear. I know it's the first time, could be a bit. So now that we have the tools to evaluate our models, the natural question would be like, should we even bother again, right? And is the machine learning models or deep learning models are well calibrated, right? And the answer is no, right? So if you look into the body of research since 2000s, people evaluated calibration of various models. At the time, they started with support vector machine was around big time in the late 90s, early 2000s. Everybody was using it for even things like computer vision. So they looked into SVM and said, it's actually not calibrated, right? Then they looked into shallow neural networks. And actually, one of the key papers made a mistake. They said neural networks shallow are well calibrated. Turned out later, 15 years later, it was just an incorrect experiment. So the neural networks are miscalibrated. In particular, deep learning, right? So when deep learning appeared 2012, after ImageNet competition, 5 years after people started to pay attention and realized convolutional neural nets are very miscalibrated. They're overconfident. So if you have like a convolutional neural net and looking at pedestrian, it will probably most likely inflate the probabilities of actual outcomes. So yeah, the general rule is nothing is calibrated by default. And even more curious, for example, if you're familiar with scikit-learn, for like 15 years was claiming on the documentation pages logistics regression is calibrated, which is not the case. Now that people like myself and others commented on social media, they actually scraped it. So logistic regression tends to be better calibrated, but there are no guarantees, and it can be very miscalibrated as well. So nothing is calibrated by default. So here's like, if you're interested, you can go into like all this literature, and the first two papers I'll talk a little bit more about like how people try to calibrate models back in the early 2000s. And then they try to kind of, especially in these regions when deep learning appears, they try to kind of calibrate deep learning. This is only interesting from historical perspective. None of that is kind of matters now because conformal prediction can do it better. But interestingly enough, this was a key paper 5 years after the deep learning kind of came to the fore. This was a big paper that looked at it and said, look, you know, we are producing highly accurate predictions, but they're actually very miscalibrated. And then people started to look at it and said, what's actually happening? How can we have a situation where accuracy is very high and calibration is not great? And it turned out that in particular in situations where deep learning makes errors, the probabilities were particularly incorrect in this situation. So for example, a situation where self-driving car would say there is no pedestrian on the road, and then there is a pedestrian on the road, the probability would be completely incorrect. So this is why you have like cases, if you look at like what's happening with Tesla. For example, it's going, you know, there were cases when it was going and there was like skyline and a trailer, and it's confused trailer for the skyline because it has no way of telling unless you kind of calibrate and apply conformal prediction. It has no way of understanding that actually this is a uncertain situation, and it needs to kind of adjust its probabilities accordingly. So if you're interested about this, my PhD thesis actually has a chapter 2, where I spend a lot of time at the time kind of overviewing the state of affairs.
Just one question.
Yeah.
How can it be that accuracy is higher in
Well, I mean, if you think about it this way, imagine the situation where a pedestrian is on the road, right? So the chances are maybe it's like 1% or like even less. So even if you do like a basic algorithm and say there is no pedestrian on the road, you get extremely high accuracy, right? It's over like 99%. But its model is not good, right? Because it's not calibrated. So, but it's actually very interesting. You know, if you're interested in why and how this is happening, this is all the kind of type of, you know, papers you would go, and in particular, Guo 2007 is excellent paper on the subject. So now that we know things are miscalibrated, how do we calibrate them, right? So this is actually for just historical overview and some of the tools that you might still use, but they come with the caution that they don't have calibration guarantees, right? So it's like, if you use these tools, there is no guarantee it can make things better and it can make things worse, right? So this is why conformal prediction has these guarantees, but it's good to be aware about these tools because they're like, people use them. So the first one is called plot scaling, and this goes back to 2001. So I told you that support vector machine was like everywhere, right? And everybody was using it for pretty much everything: computer vision, NLP, tabular data. It was the kind of the model to go right before deep learning. And Platt, who was at Microsoft at the time, he looked at support vector machine and said, you know, we know that it's miscalibrated. How do we actually calibrate it? So he did this like very simple thing. He plotted like this reliability diagram we spoke about before, and he saw this kind of shape is a familiar sigmoid. If you deal with deep learning, you probably have seen it like a million times. And he said, now that we know it is sigmoid, let's just use sigmoid function and kind of map it back to this one, right? Very simple idea. He didn't like prove any math or anything, and it kind of worked, right? Because support vector machine does tend to produce sigmoid, right? What happened later is that people didn't realize that it kind of took a life of its own. People start to use it everywhere, right? For support vector machine, which is not much used anymore, for booster trees, everything else, and it just they didn't think about it. You know, it's like it's a tool that was invented for a particular application, but they're using it for something else, right? Without thinking what's happening under the hood, right? So, and it took actually like 16 years until some other people in the paper called beta calibration proved that this sigmoid shape is actually quite a restrictive assumption, and it, you know, you have basically the same variance between classes 0 and 1, and it's normally distributed, which is like, if you are like in industry, no normal distribution, it doesn't happen very often, right? Question?
Yeah.
question about like calibration, like what actually model we can call as like well calibrated? Because like
None.
yeah, like this is the case. So we'll have like some holdout, fine. So we'll like use like holdout, like some.
No, I'll
some
teach you
set.
how to do it in a few slides if
Okay,
you.
cool.
But
I just, like, wanted
yeah, I
to
mean,
know, like,
I'm
the
just
criteria.
yeah, that's fine.
Cool.
But like the way to think about it, it's like no models calibrated. It's a good start. It's like lesson learned, right? And this is like a very important one. Yeah, this is plot scaler, so still used. Sometimes you get better results than no calibration, sometimes not. And how to check it, again, you use Braille, log loss, or like calibration diagram. So the second one which people did, and this is both available in scikit-learn, it's called isotonic regression, right? So people said, okay, this is a very simple function with just two parameters, and it can only capture like certain shape of the curve. Let's do it in a kind of data-driven way. Everybody likes data-driven way, machine learning, and so on and so forth. So what they did, they basically said, we have this kind of, again, this is like score and probability. Let's fit some curve, and let's do it in a data-driven way, right? And fortunately enough, statisticians already had a way to do it. It's called pay adjacent violators algorithms. Basically, you know, the way to describe goes from like left to right. It's very fast, and it swaps if there is like, the idea is that high score should be like higher probability. When it's incorrect, it just swaps it and kind of does this medium average instead. So now that we have data-driven algorithm, we solved one problem, but we created another one. Because this is data-driven way, it's essentially can overfit, especially on small data, right? If you know, like powerful models don't do well on small data because they basically overfit, right? So we have another tool based on assumptions. It can overfit, and it cannot improve calibration by default. It doesn't have guarantee, but it can improve in some situations, right? So the main assumption here is, because it assumes high scores result in high probabilities, it's actually kind of isotonic, means increasing in this case, right? So it's kind of growing. And if you think about this, if you're familiar with machine learning, it assumes ROC of 1, right? So in classification tasks, you measure how, you know, do kind of high scores relate to high probability. So this is like ROC of 1 on a test set. If you think about it, it never happens, right? Unless you know data distribution, it's in some cases it's 60%, but never 1. Still, I'm just explaining it because it's available in scikit-learn, and you'll see people using it, right? But what happens, sometimes people use it without checking calibration before and after, and realizing it can actually make things worse, right? So now that we covered the calibration and we talk about like models are miscalibrated, the calibration is important, right? Let's talk a little bit about conformal prediction. So what is conformal prediction, right? Anybody has heard the name before or used the conformal prediction? No?
I'm following you on LinkedIn, so
So you've seen it all, right? Okay.
I'm finally here to learn what's that in more detail.
Well, perhaps I should have followed it more, but okay, let's me try to explain it today. So conformal prediction is quite simply, if you remember, we talked about this first paper where the founders of conformal prediction said we want a way for the model to reason about the uncertainty, right? The own uncertainty, kind of all in one package. It's essentially a calibration kind of layer that we can apply to any model. And if you watch this talk that I mentioned, this is also from this talk by Michael Jordan. So he's a big guy in US, and he's like likes to talk about conformal prediction a lot. He's actually learned about it. He used to do Bayesian like framework. You probably heard about Bayesian. So he learned about it in a car to the airport from another professor in the US, a guy called Larry Wasserman. If you're familiar, he's like a big statistician. He has several books. So Larry kind of grabbed Michael on the way to the airport and said, in 40 minutes, I can explain to you conformal prediction. And because Michael is like a very smart guy, he learned it all, and he just changed from Bayesian things to conformal prediction. So essentially, if you think about machine learning, we are here. So this is like state-of-the-art model. It can be LLM, can be anything else. fancy kind of, whatever it's inside the box, and it's miscalibrated. So what we do conformal prediction here, and we get calibrated outcome. So why is this attractive? First of all, we've talked about it provides like mathematical guarantees of validity. So validity is the same as broadly as calibration. So if you think about it, like if you saw like kids play bowling, you have these barriers, right? So the kids can never throw the ball outside because it's like guarantee, right? They have this kind of thing, so it's guaranteed to go there. Same conformal prediction has guarantees, right? And it's essential for decision making because we want to calibrate probabilities, risk control, and it's very easy to do, right? This is like, this bit is very attractive. It's non-invasive to the data science model, machine learning model. You can have your model that your data scientists work for 2 years. You don't need to go and dismantle the model. You don't need to even like understand what's inside. And things like ChatGPT, for example, we don't even know what's inside. Nobody's going to tell us because it's IP. Nevertheless, you can still use conformal prediction. As long as you have access to labels, you can just apply calibration label, and you're good to go. So what is it? Yeah.
Just like for clarification, am I right that like all methods, like that like isotonic, regression, and etc., they can like help with calibration, but like they will not give you like any guarantee.
They will not. They might help, but they sometimes they make it worse actually as well.
And like the big like difference like
Yeah.
for conformal predictions, because like now we have like some
Yeah, we have some mathematical guarantees, and I'll show you like in some simple cases it's actually very straightforward math, right? And people think it's like overly complicated, but actually if you know a little bit of math, you can actually prove, the baseline guarantee in like a few lines of math. So it's very straightforward. I don't know how people missed it. They should have invented it, in my opinion, 100 years ago, because all the things were there. The statistics which is used to build the proof is already there. So what is conformal prediction? Essentially, it's a machine learning framework, right? Sometimes you see people say it's statistics. It's not actually. Neither Vovk nor Kolmogorov were statisticians. It has origins in Kolmogorov's complexity. What is Kolmogorov's complexity? Essentially, it's a way to imagine you have a sequence of points, zeros and ones, and you want to measure how complex the sequence is. So if it's like, 0, 1, 0, 1, 0, 1, it's very simple, right? It's very predictable. You can describe it in a couple of words. If it's like completely random, then the amount of words, imagine, or code to describe it, it grows it, right? So Kolmogorov's complexity is a way to capture the complexity of the sequence. So what conformal prediction does, the name is a bit misleading in my opinion. It doesn't predict anything. It converts point predictor into probabilistic predictor, right? It's non-invasive calibration layer, as I mentioned here, which is very important in particular for the industry. That's why you see like industry and researchers are applying it everywhere. And from a business viewpoint, you can just add a conformal layer and you're good to go. You don't have to kind of disrupt your MLOps or anything like that. It comes with calibration guarantees, validity guarantees, which means it's no like probabilistic bias, right? So if you're familiar with bias, if you do like prediction here systematically over, it's like bias in terms of point prediction, but this is like bias in terms of prediction intervals. So it guarantees the intervals exactly where they should be. We don't need any subjective probabilities, which is like what Bayesians create, and where there is subjective probability, there is subjective posterior, and comes with all sorts of things. And the only assumption we need is no assumption, right? Because initially people thought they need exchangeability, which is like very weak assumptions, but now it's been proven we don't even need that. Exchangeability is basically, if you imagine you have some, probability and you have like urn with balls, red and black, and you pick them up and return them back, so the probability will be the same no matter what the sequence is. It's very weak assumption. So even weaker than IID, which is like what is used in machine learning. IID means data is coming from the same distribution, basically. So, yeah, I mean, where are we now, right? So it's become a very popular topic. It's model agnostic, so you can use any model as a point prediction model. statistical machine deep learning model, LLM, transformers, you name it, you can use anything. Actually, if you're in business, sometimes you solve a problem and the business already have some kind of business prediction model like baseline, right? So they might have some rules or whatever. You can use even that model. You don't have to use machine learning. You can just augment this model to create calibrated predictions. Predictions happen calibrated for final samples of any size, which is quite incredible the first time you see it, because if you study statistics, in statistics, normally you don't get any guarantees unless you go to like infinite use case where there is a lot of data, so you have some convergence things. But conformal prediction can guarantee validity for final samples of any size, but of course the problem is then if your data set is very small, your model is not very powerful, right? So you can't train machine learning models, so your prediction interval will be wider, but it will still be valid, right? So this is like the beauty of it. Been around since '98. First book was published 2005, unknown for 15 years, and now it's pretty much everywhere. So this is what some professors have to say. I mentioned Michael Jordan. So basically, he used to do Bayesian statistics before. Now he says conformal prediction is the answer to UQ. You'll probably see this term uncertainty quantification, and the reason is because it's the best, comes with guarantee, very simple, very generalizable, and works every time. This is Larry Wasserman. He's a very famous statistics professor. He actually kind of converted Jordan, and now it's like everywhere, every university which is big in US, MIT, Stanford, pretty much every university does research in conformal prediction. And similar things, you see similar topic, how simple and general it is. So, yeah. So what is happening in terms of the mass? Essentially, it provides guarantees that, imagine we are predicting demand for a particular good, and we want to understand with 90% confidence what the interval is going to be, right? And we make a point prediction using whatever model you have. We put a conformal layer on top of it, and it says, for example, I don't know, 25 to 35, right? But it's not just an interval which you see people sometimes just create interval without kind of checking its quality. It's an interval which guarantees your future demand to be there with user-specified coverage. So if you want 90%, you guaranteed to land there in this interval with 90% chance, and it's extremely powerful because we don't know like what's going to happen tomorrow, but this guarantees us we know exactly we're going to land there, which is very, very powerful. So how do we do it, right? So there are like sometimes, I see people who start conformal prediction and they just read the basic tutorial and they think what they saw, very basic use case, is conformal prediction. And they say it's like conformal prediction model, and it's not a model, it's a framework, right? There are like hundreds of models. It's like kind of a subject, and within the subject there are various models, from very simple to more sophisticated, and to models customized to time series, for example. But a very simple way to think about it, imagine you have like a regression. So imagine you have like some data, and you take your data, like in machine learning, you usually put aside test set, right? So let's put aside some test set, forget about it. And then we split the data into training set and calibration set, right? So the basic idea is very, very simple. You train your model on a training set, you predict, means you create point predictions on the calibration set, and then you kind of compute the difference between the point and your prediction, and that gives you non-conformity measure, right? This is like what you hear in conformal prediction. For regression, this is like very natural non-conformity measure, meaning how far is your prediction from the actual, right? So we calculate this non-conformity measures on a calibration set, which your model has never seen and shouldn't seen. And this allows conformal prediction layer to basically correct and create conformal prediction intervals, right? So imagine we have calculated all those distances in blue, right, on a calibration set. And, okay. So then we just do like a histogram, and we say 95% chance that our points are going to land in prediction interval. We just read off this number. and we put up this number on both sides of your point prediction on any test point. We just add whatever is 12.5 here, both ways, and you're done essentially. So the basic idea is extremely simple, right? You know, it's also not a very hard thing to prove mathematically, but the magic of it works, right? Every single time, because it's guaranteed by math, right? It's not empirical. It's not something that is created. It's, you know, if you do it this way, you're gonna have like lower and upper interval. So this is like prediction from your point model, and this delta that I showed you, you just add and subtract to create lower and upper bound, and then you see actuals, and they'll be like guaranteed to land whatever the confidence level you selected. So if you don't believe me, try it on your own, and you'll be amazed. Yeah. So just make sure your data is more or less exchangeable. If it's not, the race becomes a bit more complicated. And you know, if you read my book, it explains how to deal with this. But the first time you see it, it's just like, what's going on? So I remember when I was like starting my PhD, and Wolf was explaining to me these concepts, I was like, what's going on? I studied math, statistics, and like, what's going on? It's like alien math, right? But it works. So let me just see if I can get back. So let me just, okay. So we covered the basic idea. Now let's come back to calibration a little bit. So we know what calibration is. And if you look at the practical side, if you run like scikit-learn, you're probably familiar, predict proba, it's actually not a probability. If you go into GitHub repo, actually people mentioned it on scikit-learn 10 years ago, but the developers were kind of quite lazy to change it, and by the time it's everywhere, people, when they start machine learning, they think it's probability, it's actually not, right? And there are like lots of articles which explain they are not, they're class scores. The name is misleading in my opinion. It doesn't help people who start machine learning. It's grossly misleading. So what we need instead is a calibrated probabilities. So we saw plot scaling and isotonic regression. They don't have guarantees and can make things worse. How do we actually do it in a conformal way? So I'm gonna skip that. I'm just gonna go back to this one just to remind you guys what we saw. So remember isotonic regression, we just have a calibration set where we're plotting kind of frequencies of point versus class scores, and we try to fit this curve, right? So what conformal prediction does is using the kind of main conformal idea, which is a bit weird when you first hear about it. Imagine you have a test point, right? And test point can have a label of 0 and 1. You don't know which one it's going to be, so why don't we use both, right? So we apply, say we put another point, and we say it's going to have like class 1, so there will be like one cloud, we do it for class 1, and we do the same for class 0, right? Which is like when I first saw it, and it was in a regression context, like Wolf was explaining, like you're drawing a point through the label that you don't know, test point that you don't know. So of course it can change, right? But that's the whole idea, because if you do it this way, you kind of recover guarantees. So what's happening here? And this is one of the models that we obtained. And this is like my recommended model that I recommend people to use for classifications, called Venn-Numbers, right? Venn-Numbers, it's a model within conformal prediction framework. If you're wondering where it comes from, there is Venn prediction, which is kind of also quite interesting, but I'm not going to explain on that. It's a bit involved. But Abers is basically the name of the statistician that published the book that invented this kind of algorithm that fits isotonic regression. So essentially what you end up with, you're basically doing isotonic regression twice, once assuming a label of 0 and once assuming it 1. So you end up with probability interval for probability, right? And this is calibrated, right? So it gives you two things. First of all, it gives you calibrated probability, which you can recover like that. This is upper probability of class 1 and low probability of class 1, not 0, right? So this is like where people get confused. But more importantly, you recover another very interesting thing. I'm going to skip this one. This is from Wolf's paper. And essentially, I'm just going to say they demonstrated. They of course proven it has guarantees, but they also demonstrated it's better than plot and isotonic regression in most of the cases, right? And there are other papers that show it as well. But another important thing, I don't have a slide on it, you end up with like probability interval for probability, which is very, very powerful, because say you are predicting whether a patient has cancer or not. So instead of saying 0.9 no cancer, you end up with something like 0.85 or 95, or like 75 to 1. And it's a big difference, right? Because you immediately see the width of this interval shows you how hard this particular prediction case is. So if it's like very narrow, you're very certain, right? If it's more wide, then the doctor can actually consult another professional or send patient for some tests, right? So this is actually very, very powerful, and it can help you to diagnose the underlying machine learning problem, not just to kind of quantify and set it. So let me show you guys something else. In regression case, we're interested from going from point prediction to intervals, which is conformal prediction can do, as I showed you in this very simple case. But it can also do another very amazing thing, which is produce the whole distribution for every test point, right? So not only you get an interval, but you get the whole curve, which is cumulative distribution function and probability. And you can pick up any quantiles from there, or you can select any intervals, or more importantly, perhaps in finance, it's quite interesting what is the risk in the tail. So when you derive this curve, you can do pretty much everything because you recovered the whole distribution. You can compute value at risk, for example, or like expected value of risk in the tail, many things. The beauty of it is it's well calibrated in a sense. You know, I'm not gonna kind of dwell into it, but it's kind of in the right place with the right shape, right? So very, very powerful. This is like what my most of my PhD dissertation was. We published a first paper creating these things for linear regression. And of course, in conformal prediction is, you know, not very easy to invent a new thing, because not only you can create something, you have to prove validity. So we mathematically proved validity, and we proved validity for kernel regression, which can capture any distribution. And then finally, we adapted it to any model. You can put deep learning underneath, you can put transformers, you can put anything. And it's called conformal predictive distribution. You can actually do these things very easy in a library with just a few lines of code these days. It's very simple. So I'm going to skip this one. It's like a bit more messy. So we've talked about how we evaluate calibration, right, in a classification case. Now the question is like, how do we evaluate the quality of kind of CDF when we produce the whole curve in a regression case, right? And turns out there is a good metric for this. It's called CRPS. It's basically proven to be proper scoring rule, which means if you use this metric, you kind of encourage your machine learning model to output predictions in line with true data distribution. How does it work like, you know, forget about this integral. The idea is very simple. If you have a test point on a test set, you know exactly where it is. So probability of test point being below is 0, right? And above is 0. So, you know, when you look at cumulative probability, it becomes like a step function, right? But in reality, you produce something like that. So you want just to measure the distance between these two. And this is how you use to quantify probability of probabilistic predictor. Interestingly enough, some very advanced companies already started to use it for things like demand prediction, because they're going beyond intervals to predict the whole curve. And the reason it matters for them, like sometimes interval is not enough, right? You want to understand the whole distribution because you want to see like what is the probability of high demand, so you don't end up with stockouts and things like this. When you recover this curve, you can calculate service level for any kind of distribution, meaning that you don't have too much stock, which is very expensive, right? It's up to 30% of the stock value. It's warehousing cost, inventory, and so on and so forth. And you don't have too little stock, so which just means your customers are going away. In B2B, this is even more important, right? Because if you're going to Sainsbury's regularly and buy you like, I don't know, packet of crisps, it's not there, you're not going to be very upset, right? if you're like in manufacturing, like I worked for a manufacturing company where we did, produce things for automotive or like aircraft or things like that, if they have assembly line and we don't ship them things for manufacturing, every minute is like 100,000 euros stoppage. So they're not going to be very happy about it if they're out of stock, right? They're probably going to go somewhere else forever. Right. Any questions at this point? So I covered mostly like table data, maybe two more exciting and simple things. Yeah, please.
Question from my side, like, does it mean that like in production, for example, we can use like two scores, like confidence level and just like actually like score, like how like the output, the model calibrated output of the
Yeah.
model. And looks like for regressions that you show, like in some like area, like model can be like super confident.
Yeah.
Maybe in another, maybe
Yeah.
not like really confident.
Yeah.
And also it could be like some kind of like metrics to understand like how good our model. So like in case like all predictions are like in high confident like
Yeah.
area,
Yeah.
that's mean like model is powerful.
Yeah.
If it's like distributed in low confidence zone, it's
Yeah.
you need that like more features.
It depends upon your use case, right? And it's a very good question. I can give you an example. I'm like building now a system for my company which predicts aircraft being delayed during engineering issues, right? And essentially, what we are interested in surfacing like top X aircraft on the day that people can fix, right? So I'm very interested where it's calibrated at the top level, right? Because I'm interested in recall, right? I'm interested in surfacing, aircraft or patients or things at risk. I'm not interested in the kind of low signal zone. So it's all like very use case dependent. But what's important is in terms of metrics for both point prediction and probabilistic prediction, you have to use correct metrics, right? If you're like, for example, imbalanced data, you can't use accuracy because, if you're like 99% use cases, points are zero, you just say zero. It's like, it's not very useful prediction. You want to kind of find the ones which are actually won, whether it's fraud or like customer churning, right? So for probabilistic prediction, the recommendation is to stick to proper scoring rules because they have good qualities, which guarantee the model will kind of produce predictions which are kind of honest and on your real data, right? Not something else. Which means for classification, the good practice is to use both Brier score and log loss because sometimes they give different directions, and only use like reliability diagram for visualization. For regression, you'll see things like Winkler score, which is basically approximation of this CDF CRPS I showed here. So I can provide more like information if you're interested. Yeah, ping me on. So let's talk about like deep learning, fancy stuff, right? Everybody loves pictures. So what do we do actually in like computer vision, right? So in computer vision, deep learning took off in 2012 when ImageNet competition, where there was like 1,000 classes of pictures and people were running it for many years. This is for the first time where deep learning won with like big uplift in accuracy, right? And a lot of companies started to be interested. GPUs were like everywhere. People in Facebook, Google, a lot of money went into this research. But the idea is the same, right? We have a point prediction. We want to model to reason kind of about how confident it is about this prediction. And in computer vision, what they do is usually they look at prediction sets, right? So in tabular data, it's not recommended. You just do calibrated probabilities. But in this case, you see we are going from left to right. Left case is very clear. It's a fox squirrel. I'm not an expert, but people say it's a fox squirrel, right? The middle one is like still quite clear, right? It's just turned a little bit, But, to kind of ensure the actual label is within, we have to kind of expand the set because there is probability. Maybe somebody kind of marked it as a bucket, right? We don't know who was marking. Maybe they decided to go for bucket. And in this case, it's kind of partly occluded. And it's not very clear what it is. So some people say it's marmot. I don't even know what marmot is, or fox squirrel, right? So the idea is like you have prediction set that captures actual label with user specified confidence, like 90 or 95%, right? So this is from my book. Actually, I have a chapter on computer vision, and you know, I kind of run some of the models, conformal prediction models, and just showing you like what pictures labels could be. The first one is crutch, drumstick, perhaps not, plunger and swimming. You know, so you see, like if it's like less clear, you can have a few labels in it, right? I don't know to show you. Actually, this one is sandal, running shoes, perhaps not backpack. There is a possibility it could be running shoes. We don't know, right? Data tells us backpack, small probability, right? It's like, yeah, people marking stuff, right? So the idea is like we have to kind of create a set which is again calibrated. It's guaranteed to include true label with specified probability. And as the picture becomes more uncertain, we have to expand it, and the probabilities on the top class are kind of dropping, and other classes can appear. So conformal prediction for time series, right? It's been an incredible success story. So initially, people created conformal prediction for exchangeable data, so you can swap the data in a way. In time series, of course, it's not exchangeable because you can't just swap, you know, the data. Temperature at night is not the same as temperature at the day, so the structure matters, right? So they started to develop models for time series in 2021. These amazing people in Georgia Tech, you know, they did a few first papers, and it just kind of took off and got a life of its own. So what happened since then? It's actually in just 3 years, it went from nowhere to a lot of research papers. I think about 20, 30 now, and even more importantly, perhaps, what was kind of hindering the, you know, the adoption of conformal prediction. First of all, it was unknown; nobody knew about it, like until, you know, I was talking about it for so long that people started to pay attention. And then second thing which happened, there was no libraries, right? I know a lady who used to work in London. She's now, I think, in Germany. She worked for insurance company, so she implemented some conformal prediction models by hand, 2017. And it was like her talk on Pi or whatever, big Python kind of conference. I like reached out to her and like, how did you do it? It was like, no. She was a mathematician. She just implemented it by hand. But nowadays, everything can be done just with a few lines of code. So, and in time series, you know, if you're familiar with forecasting in open source, it's actually like all the big forecasting open source packages have conformal prediction as a standard now, right? So it's incredible, yeah, absolutely incredible. So even more interesting stuff, for example, right, going beyond tabular data. Here we are looking at MRI, right? So it's a health perhaps application. So if you're familiar with like MRI, it's basically a tube you have to lie down for like 40 minutes, right? Not the most pleasant experience, but the reality is that to take a full MRI scan, I think it takes like 8 to 10 hours, right? So what mathematicians did, this chair of mathematics and statistics, Emmanuel Candas, he's like very good mathematician. He's also doing a lot of conformal prediction research. So like 15, 20 years ago, he did this kind of reconstruction of partial scan. So people only spend like 40 minutes in the tube, but then he could reconstruct the data like they spend 8 hours, right? So it's actually patient experience dramatically improved, right? So we get a picture here. This is like where mass happens, and he proved that mathematically you can reconstruct. But then again, we don't know, right? You know, we don't know. We need the image with uncertainty, right? We don't know which areas are more uncertain or which are not. And this is called image-to-image regression, right? So actually you fit image and you obtain image, right? From here to there. So what conformal prediction does, it's a layer on top of this, which can actually turn this into like uncertainty picture. So you see there are various areas of uncertainty. Kind of blue is low uncertainty, high uncertainty, and red is kind of quite uncertain areas. So if the doctor is looking at a particular thing and he sees like blue, the doctor can be confident, right? So it's a good outcome. If it's like red, we probably need a second opinion, or we need biopsy or something like that, you know? So it's extremely powerful. So, anybody can tell me who is that? No? Any guess? Ah?
Elon Musk.
Okay, so this is, let me just play it. I actually quite like this paper. I think back in 2022, It was called confusion, and it's basically creating, like, if you like, uncertainty intervals on the reconstruction of the picture. Let's see what happens. So yeah, this is like lower bound, upper bound, ground truth. So it's pretty good, I would say, right? That's another one. Who is that? Anybody know?
Lower bound and upper bound in which sense?
Well, whatever sense they use in computer vision, right? I don't know. But it's kind of, it has to be like similar to ground truth, and so this is also similar, but not quite that. Yeah, I mean, if you're interested, read the paper. It's quite cool paper. They have a website, right? So quite interesting things, right? So about NLP, right? So I'm only like scratching the surface here because I'm not a LLM person yet, to my like embarrassment, right? I'm trying to learn about them. But it's become very popular tool for LLMs and NLP. And if you're familiar with LLMs hallucinate, right? So which means they produce overconfident predictions with high confidence, but they're actually incorrect. So conformal prediction is ideal to somehow mitigate the hallucinations. And a lot of papers, I'll show you in a moment what we have. But just a simple example, for example, you know, like this is like decision support systems that they have, I think, in medicine since 20th century, late 20th century. So, you know, if somebody says, I have these symptoms, should I take Xanax, right? Xanax is, I think, American drug for anxiety, so people prescribe it all the time over there. But perhaps not so lightly, right? So you need to kind of be confident how really you should or should not take Xanax. And then you put it in, and conformal prediction says it's actually like uncertain. There's not enough information, right? Or maybe the model is not so good, so maybe consult a practitioner, right? So just a simple example. So this is pretty cool. I think this is from last year, and I told you like it went first big in academia, so almost like every major university is doing research in conformal predictions, and it's kind of spread to companies. NVIDIA has 600 PhDs in their like R&D center, and not this year, but last year it was one of the key topics. They're actually investing a lot into conformal prediction for self-driving cars. I think they're creating something that they can license to other companies. Amazon published papers on recommender system, which was quite interesting as well. Apparently you have to, if somebody is buying shoes, you have to serve them like a prediction set, and it has to be accurate, so they pick something from the set. And like, if they don't know what size it is, right, you have to serve them like, you know, size that more or less, fit for the customer. But this was rather cool, right? So this is actually LLM-powered robot. So the human gives, I'll just explain a sec what happens. Human gives extra instructions to LLM, and then robot executes instructions. And you know, coming back to the original thesis, like in '98, we have to have machine reason about its uncertainty. So there could be situations machine is quite certain it would execute. Machine is uncertain. Perhaps machine should ask for help for a human. Let's just watch for a brief moment what's happening here.
On a small counter in a microwave.
So it's a vision module. It sees like.
Should I pick up the metal bowl or the plastic bowl? Pick up the plastic bowl, please.
So here is a consequential application, right, where the robot is faced with uncertainty. It's been told to pick up a ball, and it goes there and sees two balls, right? And the reason it's consequential because if it picks metal one, puts it in the microwave, nothing good is going to happen. So, you know, it understands using conformal prediction that its uncertain situation needs to consult back the human for additional instructions. This is exactly what's happening. This is from DeepMind in Princeton, quite a nice paper. And we're almost coming to an end. So there is like lots of applications to pretty much everything, you know, GNNs, graph neural networks, LLMs. You know, if you followed LLMs, it's quite a success story. But for example, what was happening initially, I don't know now, but you know, they gave it like exam questions, right? And LLMs were not doing particularly well on hard subjects like chemistry, right? and one of the reasons was that it was basically hallucinating and producing an incorrect outcome. When they applied conformal prediction, it basically equalized outcome, right? So it's kind of improved the situation quite substantially. This is quite nice example also, like if you use LLM, you know it hallucinates, right? And then the hallucinations are more prevalent in the topics it doesn't understand about, right? For example, like when I was writing my book in 2022, LLMs were already around, right? But it was still not enough information on the web about conformal prediction. So while asking a question, it was just basically consistently producing incorrect information. So, and I noticed that if there is some like less known area, they don't have enough information. We have this, remember, aleatoric and epistemic thing. So not enough information basically means not enough knowledge. So they hallucinate more. But this is like an example where it hallucinates and conformal prediction is applied to kind of clean up the text, right? So this is after conformal layer, it removes all the incorrect information. It's kind of ends up with quite a nice output. So yeah, finally we come to the end. This is basically the resource I created. I mentioned to you it was quite popular and kind of conformal prediction with exponential. I spend a lot of time supporting this. I think it has like 500 papers now. All the libraries are there. Tutorials. If you like to start, you can just go and find it. The topic that you're in, it's like hundreds of people look at it every day. I know like researchers across the planet use it quite a lot to kind of just identify subjects that they're working on, right? And it's free, right? So it's there. So this is a book I published 2022. I just learned 2 days ago. It was translated into Russian and published in January. So it's actually in you know, like Ozon and what's it called, Blackberries, right? Russian Amazon, and even Biblia Globus, which is I'm quite proud about it. Saying, and this is a new one, right? So yeah, some people said it was translated by ChatGPT. I don't know. My Russian is not so good anymore, so I cannot tell. I know it was professional translated by a guy who actually does it all the time. I know him. Probably not. Yeah. So yeah. Actually, it was a funny story because you know I asked the publisher, and I don't work for them anymore, but they keep the book. You know, that's going to be my new book. I asked them to translate it into like Russian, Chinese, and Portuguese because it's like big in Brazil. So they were like, they're not great service. They were just doing nothing. And then I was talking to this guy, and he said, "Oh, you know, the publisher got the book, and it's like." They're not so sure whether to publish it. And I was like, I didn't know it was translated and published, and I looked at it and it's like out of stock everywhere. And so yeah, interesting story about this translation. And they sold the rights to DMK, I think, for $800, which is the cost of. I think the book in Russia is like $50, right? So you know, it's because they exited Russia, right? So they just. You know, sold all the books and exited, right? So yeah, and I have this course. Maven is basically like professional platform. It's like a premium platform, right? So it's not cheap, the course, but there are people from like industry from US for whom it's like, you know, it's good value, and it's a live professional kind of cohort with nice people, usually like hedge funds and people like that. So. Yeah, resources. Again, all of that is on my it's not my verse. Somebody said about it, so it's on the repo, and there is many more things there, right? So if you're interested to learn, I hope it was useful. Yeah.
Practical questions.
Yeah.
So the first one, you said your conformal outperform. Distribution. So imagine you have
This one?
Yes.
Okay.
So imagine you have a multi-class classification problem.
Mm-hmm.
So the base model will outperform, say, with a neural network and softmax
Yeah.
activation of the last layer. So you get probability distribution for each class.
Yeah.
And if I add your conformal prediction, I'll get for each class not only one probability, but range of probabilities.
You'll get a range of probabilities for every class, and this is actually,
Certain.
yeah. So that's, but you can also compress them to one probability for each class, and they will like calibrated, much better calibrated, if that makes sense.
Say 95%.
Yeah, yeah,
probability.
yeah.
So if I want a range, I
If you want a range, you keep a range. Yeah.
Okay, very
Yeah.
good. The second question, you said it's a framework, so it's a kind of layer. So
Yeah.
it's a last layer, so I can add your layer to my
Any model.
network.
Any model.
How to do it practically? What's the name of your framework?
Oh,
Where
okay.
Where to take it?
But yeah, how to do it practically is, there are different models for different use cases, right? So if you look into my book, I cover like the most popular methods for every use case. Say, for computer vision, you have like a menu of methods that you can select from, right? And you can kind of create them with a library in just a few lines of code, right? If you
It's just a custom lambda layer.
Yeah.
With your implementation.
yeah,
Okay.
depending on what you use case, whether it's classification, regression, or time series.
I need it for multi-class
Yeah.
classification.
Well, multi-class happens to be my first PhD paper, which is like basically extension of numbers to multi-class. So, and it's if you go into this one, right? So, for example, I mentioned numbers, right? Which is the way to do it in binary classification. There is a nice library which is like PhD student before me created one. And he has implemented both binary and multi-class, which is my paper. So if you just go like on my repo, find the numbers, you can just take this library. It's called the numbers, and just run it. Pip install, and you're done like in 2 minutes. And not only that, you can actually apply it if you already have a trained model, right? So you don't need to train him. Yeah, you can just feed it like labels for your multi-class, and it will create the outcome for you. So that's but you can ping me on LinkedIn, if you have any questions. I can always direct you to specific use case. No worries, yeah, sure.
I'm trying to use now isotonic regression, and it works. It gives me much better results than without it.
But how do you know that you get better results? Are you using the metrics?
Just by profit for the period.
Huh?
Just trading using
Okay.
isotonic and
Okay.
30%.
Well, I mean,
It's a simple method.
yeah, you mentioned it's actually quite interesting if you have like some models for betting, like on horses, right? So instead of like your score, you'll get an interval, right? And if your interval is very narrow, it's probably an easy solution, right? If your model is expanding interval, it means there is actually quite a lot of uncertainty. You probably wouldn't want to bet that much. So actually, it's quite powerful. I know some hedge funds using it already, things like that.
My current algorithm is I use a model to predict probability distribution of three classes.
Mhm.
Then I use it in a simple method algorithm. I calculate the expected value of each model with some threshold.
Yeah.
I use it as a signals to trade or not.
Yeah.
So to bet or not.
Yeah.
So,
And this is actually,
Isotonic helped me with it,
yeah.
but I really need range.
Yeah, and this is what exactly what you need, because in trading, it's quite hard to create good models. But actually, where the kind of secret sauce comes in is you have a signal and you kind of quantify so that you decide whether you trade or not, right, on this signal. If it's strong, you trade, right? If it's not, you don't trade, right? Or you go in opposite direction. This is what it helps you to do. But of course, mine is that, if you have like a time series, things start to change, right? So you have to be careful. This is, this specifically is for tabular data with the same distribution. You need to monitor your distribution as well to make sure that it's, yeah.
Don't work with time series because it's a football match. Just simple one
Yeah. 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 So you can find a lot of like knowledge in my repo or like my book, which is available, anybody can use, but kind of more sophisticated cases, like I mentioned, I helped startup in the City of London to put intervals around time series for predicting macro, and this is like IP, right? So it's nothing too sophisticated, but it's not covered like specifically. You have to do a bit of like extra work, right? I'm gonna put it this way.
What kind of challenges do you see to make it standard, like industry standard?
I mean, I think it's just going exponential now, right? It will take some time, right? But it has a lot of attractions, right? I think the challenge is more like industries understanding that they can get actually much better outcomes by quantifying uncertainty rather than doing point prediction. Because the way, like you hear people say, forecasts are always wrong, right? That's true for point forecast because you're always wrong, right? If you kind of change the frame of it and you're talking about probabilistic forecast, right? If you just create a model for probabilistic forecast, it will be wrong, right? But conformal prediction makes it right because 95% means 95%, right? So it's a question. It's like I think it's like more general. Like if you're in industry and you deal with stakeholders, quite often they're not very sophisticated, right? So you have to. There could be two situations, whether they just trust the solution and you can go as complex as you like, just making sure it delivers them what they want. But sometimes if they're like a little bit more challenging, they would ask you, I want to understand this and how do you, this becomes like trade-off, right? You have to provide them something which is still accurate and explainable, right? But there are models out there already, like in banking there is inherently kind of explainable models which are almost as powerful as like boosted trees and things like that, So yeah, I mean.
Like what I'm thinking, okay, we can just like dive deep in like more complex models, like just like new features, like whatever.
Yeah.
But like instead of it, we can just like apply like additional layer, as they described, and have like some
Yeah.
better like outcome. But I assume we need to have like some use cases just like to show to the business that
Yeah.
this like makes sense and we just need to implement.
Yeah, but you like with stakeholders, it's like the language that you talk, right? Like I mentioned, everybody understands the money, right? If you talk about the money, they're not interested in like in a good rock oak or something like that. They're interested in the money. How much is the money? Show me the money, right? For money, you need probability, right? Things like that. They might not even be interested what under the hood, right? As long as it kind of delivers them results and the money. This is the way it's, yeah.
And time, money and time.
Money and time, yeah. Time, yes. Time is another mistake many junior data scientists make. They just keep going, and building something, and then they're out of time, right? So you need to move fast. You need to do POC fast that works, right? And then you put things into production because things are expensive, right? So if you ever worked in, especially with consultants, the rates for consultants in the UK, talking about hundreds of pounds per day, right? You can't be slow.
I think a very small percent of professional data scientists knows what is calibration.
Yeah, true. But
It's not an industry standard.
it's not an industry standard. But it's like, for example, I know like on social media, on professional media, and maybe it's just people I follow, and I saw there is very, the standard in terms of understanding calibration has improved dramatically, right? You wouldn't see people talking about things that they were talking about. Now a lot of good people understand what calibration is, right? And things like, for example, if you're familiar with like imbalance data, right? They do like undersampling or oversampling. Like before, people would do like SMOTI and things like that. Nowadays, you only see people who are saying, okay, let's use SMOTI, and it's already known doesn't improve things and it miscalibrates things. So if somebody posts about it, you see this like very junior people who are not very, not very people who are like already there. They know like more about this matters for sure.
A lot of time trying to find enough information about the topic, and
It's no good information.
It's, all
This is,
that's like
yeah,
known that
yeah.
it is, and study a lot of information.
This is, I think, it's a general issue with data science because I studied physics and math, right? In physics and math, it's impossible to get almost things wrong if you like go to university, and you read textbooks. Like you learn correct things. In data science, people start and they go on YouTube, and there's some YouTuber talking about who knows what, right? Or like Medium, and they just learn things incorrect because it's just, I don't know how to change this is impossible.
It's quite funny actually how little people care about model calibration.
They don't, yeah, they don't.
Machine learning papers, for example, I've never seen anyone
Mm.
report like calibration metrics.
Mm.
And what I'm curious about is, do you have any numbers, say about some famous models? I just want to have a notion how much uncalibrated they are.
I don't know.
Because you mentioned
Yeah.
uncalibrated.
But I can tell one thing I can tell you is that I usually talk about like consequential applications like health and so on and so forth. I was actually writing one post about this, and I was like, a guy who used to work on Facebook, he said Facebook actually cares about calibration a lot, and I was like, why would they care? Because they're like just virtual company, right? The risk of making things wrong is just zero. It turns out because they sell adverts, right? They run bids, the bidding kind of companies bidding for adverts. So in order to make this bidding engine correct, they want to estimate correct probability of bid being successful. So they do care about calibration a lot. And I think I'm not so sure what they talk about, what they're using these days, because they don't talk about this like IP. I think they were like creating some ad hoc methods which were like getting them close, but of course they never have guarantees, right? So maybe this conformal prediction, right? For example, like Microsoft has been using conformal prediction for anomaly detection. It was actually running on conformal prediction anomaly detection module since 2012. So some companies knew about it a long time ago. Like pharma companies are now all over it because they suddenly discovered it, like Merck and Pfizer, everybody. They're hiring people actually with like PhDs from conformal prediction from US top universities. But some kind of companies like AstraZeneca, they knew about it for a long time because I think for some very, very curious reason, I don't know even why, the second community was after UK was in Sweden. So in Sweden there is kind of second school of conformal prediction who learned from UK, and these guys worked in health a lot, and they also worked with AstraZeneca. So AstraZeneca has been like for a long time using the conformal prediction, and the prime case was basically discovery of new drugs, right? So when you create new drugs, basically a lot of things happening. One of them, they design molecules and then they have to test it to the lab. And the things they're looking for is whether the drug works and whether the drug is not toxic, right? So before they were doing it manually, and it's very expensive and lengthy process. And after they applied conformal prediction, they basically did this funnel, right? So they kind of turbocharged the speed of development. And I think now they're very upset because the competitors know all about it. It's not just them anymore, right? But they were kind of doing it for 10 years before everybody learned about it. Now they have like big events where Pfizer is sponsoring this kind of talks about conformal prediction. They're on YouTube and so on and so forth. So yeah, it's all about like what people want to do, right? There are better tools to make things better, right? Whether they use them or not. It's yeah.
But I have impression that also people like in academia don't care so much about model calibration.
Oh, academia.
Why is that?
I don't know. I think academia is like sometimes people who there are like people who care about things, and some people who build their careers about some things, right? For example, like some academics would be using like Bayesian methods, and of course it's not calibrated, right? But because in academia things work in certain ways, if you already build a career in something, you cannot just pivot because you have your communities and you have your own like when I when I was studying my PhD, right, I started PhD with Wolfgang. I wanted, I just finished masters, and it was like reinforcement learning was all over the place, right? Like DeepMind was doing this kind of, Atari games and everything, and I kind of, UCL was very close to DeepMind. This is actually where the founders came from. And I was like, why should I do this conformal prediction? Nobody heard about it, right? Nobody cares. I don't even understand. It sounds like Elon Musk to me, right? But, he does it, and that's one of his main topic. If you are doing PhD, it's very rare that you can just, do something else. That supervisor has to be interested, right? But ultimately, I got, it was good for me. I enjoyed it, and I decided to promote it, and it paid off, right, in a way. So if you have a lemon tree, make a lemonade, right? So now it's everywhere, right? But with academia, if professors, I know that, if professors are already in their career, like mid-career, they will not pivot. Yeah. I was doing some research on commodities with one person, and he was out of PhD, I think 5 years, right? But because his supervisor was using statistical models, he wouldn't do machine learning, right? He had a certain way he wanted to do things, and I said, oh, let's do machine learning. Let's do machine learning. No, let's do this and this. Then we go and to conference in US, and there is, I forgot, it was like one big university. They started to apply machine learning to this research kind of domain, and they got very famous, right? But they were smart about it, right? They started to use things which were better. But in academia, sometimes people are like, they start to do things, they're already famous there, right? If they started to do something else, it's a big risk for them. They might not succeed, and they're already good at something. Why would they use something else, right? It's an interesting situation, yeah.
People follow social trends or something.
Exactly. Yeah. People follow social trends. Humans are social animals, right? So they follow trends.